Good morning. This is Engineering Statistics and Linear Algebra 18 EC 44, Module 2, Lecture 5. So we are studying the chapter Multiple Random Variables, and after that we are studying the sum of two independent random variables. In the Lecture 1, we studied about the bivariate, PDF and CDF. Also in the Lecture 2, we studied about the bivariate expectations. Then the Lecture 3 corresponded to the bivariate transformations, and then we had the Lecture 4 for the Gaussian bivariate random variable. So now we are studying the Module 2, which the Lecture 5, which corresponds to sum of two independent variables. So we consider here the general class of variable, general class of problems where we consider the two independent random variables. So W is equal to, again, we consider the random variables to be independent random variables to be added, x plus y, where x can be a signal random variable s, and y can be a what we call noise random variable v, and the signal and the noise can be independent of each other. In general, we can also write that the what we call independent random observations of a same random variable x can also be considered, where we consider where we say w is equal to x1 plus x2. So under those conditions, if the mean and the variance of the random variable x and y are known, then the mean and variance of w can be calculated using the linear properties of the expectation operator in the 2.58 and 59. That is, EW is equal to E of x plus y. EW is mu w. E of x plus y will be nothing but EX plus EY. That is, mu w is equal to mu x plus mu y. Similarly, the variance can be considered as, sigma w square is equal to E of w minus mu w whole square, and w can be replaced by x plus y, and mu w can be replaced by mu x plus mu y. Then this will become x plus y minus mu x minus mu y. So then we can join this x minus mu x over here and y minus mu y over here, and then expand it, because we have a square here. So x minus mu x square plus 2 into x minus mu x into y minus mu y plus y minus mu y square. So expectation of this quantity is nothing but sigma x square. Expectation of this quantity is covariance of xy with 2 as the coefficient. Expectation of this quantity is sigma y square. And because xy are independent of each other, we say that the covariance of xy is equal to 0, because they are independent, and also once they are independent, they are uncorrelated. So therefore, once we know the sigma w and the sigma w square and mu w, we can find the fww, that is the CDF of the random variable w. So CDF of the random variable w will be equal to P of x plus y less than or equal to w. So this involves the bivariate random variable x and y, the region R over which x plus y is less than or equal to w is illustrated in the figure, which is written over here. X plus y is equal to w is this line. X plus y greater than w is this region above the line. X plus y less than w is the region below that particular line, which corresponds to x plus y equal to w. So therefore, the probability of x plus y less than w is equal to P of x comma y belonging to R, that is the double integral of the what you call joint probability density function of x and y variable together, f of xy x comma y dx plus dy. That is given in the 3.14. So this again, you can just substitute the variables for them. That will become minus infinity to infinity, and this is minus infinity to w minus x, f of x, y, x comma y, dy dx. And this quantity is fww in the earlier equation over here, in the 3.81 over here, and hence we can just replace that by the fww. We can replace this by fww, where this is the CDF. Now, if you differentiate this equation d by dw of fww, you will get the PDF of the w, which is small fww, and the differentiation is with respect to the w there. So w is the variable only here. So d by dw can go inside of this. D by dw can go inside of this, and d by dw and the, the what you call integral will cancel, and effectively we will be left only with this, with y being replaced by w minus x. Y being replaced by w minus x, because there cannot be a y variable here once you do the integration. So that's why f of x, y, x minus w minus x dx will be the final statement. And this is nothing but what is, this can be, because x, y are independent, you can just write fxx, fy, w minus x dx. And this is clearly what is known as the convolution integral. So this is the convolution integral, and then also we see that you can just replace the x and y variable. There we had, fxx, fy, w minus x. So what it means is fxx is the state term, and fy, w minus x is the, what you call, we take the, so to say, the value of, invert that fy of x to fy of minus x, and then shift it by the w. Here we just do the other way around, that is fyy we take, and fx w minus y is what we are considering here. Earlier this was fxx and this was fy w minus x. Now it is the reverse. So whether it is convolution of fxx with fyy or fyy with fxx, both are just same. So it does not matter which factor in the integrand of the convolution integral gives the shifting and rotation. So taking a negative of this will just correspond to the, minus x will be corresponding to rotation, and adding it to w is shifting. So which is the term which is shifted and rotation does not matter, and hence we will just write fww is equal to fxx star fyy. So one of them can be shifted and one of them can be kept as it is. So says the PDF for the random variable w is equal to x plus y is a convolution of the PDF for x and y, a convenient relation for the characteristic function. We can try to write the relationship for the characteristic function of w like this, okay, using the relation which is 2.38, and we can put it in the we can put the 3.83 into that, 3.83 into the 2.83. So 2.83, let us see what it just corresponds to. So this is the, characteristic equation. So in this characteristic equation, we need to substitute over there the term which corresponds to fxx. In the same way, we can substitute the value of fxx there. But only that now it is a two-dimensional variable. Okay. So hence, we will get here the double integral of, the term which is written over there, the single integral minus infinity to infinity, and this is f of ww of dw. F of ww is written directly over there, and e to the power of j omega w is also there. Okay, so to 3.83, which is here, is substituted in the place of fww. and then we'll get this function. Now we can, just take this fxx outside, because there's no w term there, but w term is there in fy w minus x, so therefore it should be within this integral. Now we can write the change of variables with v is equal to w minus x, or that just means that we can substitute for this w minus x plus x. In place of this w, you can write w minus x plus x plus x will cancel, and w minus x will be equal to, substituted by the value of v, so therefore it will become v plus x, and then, so that means w is replaced by v plus x. So x goes out with the fxx because it is not dependent upon w, and because v is w minus x, we are just keeping it inside the integral. So therefore, this will become e to the power of j omega v dv, because w is equal to v plus x, dw will be equal to dv. So from this, you can clearly make out that it is just multiplication of the one-dimensional characteristic equations. One-dimensional characteristic equation. So it just means that the what you call convolution in this statement will just give you in the characteristic equation the multiplication, right? The convolution of two different variables, two independent variables, will correspond to fww, whereas the characteristic function of the w function will just be the multiplication of the individual characteristic function of x and y. So convolution turns out in the form of, it's similar to saying that whatever convolution is there in the time domain will be equivalent to the multiplication in the frequency domain. So let us take some examples. The characteristic function of an arbitrary Gaussian random variable x is, we can consider in the appendix A as this value, right? So assuming that both x and y are arbitrary Gaussian random variables and they are independent, then we will have the, whatever expressions we have written for w, we can replace it by that is mu w. For this, if you write w here, this will become w, and this also will become w. Sigma w square mu w. Mu w is nothing but mu x plus mu y. Sigma w square is equal to sigma x square plus sigma y square. And that will be the, so equation 3.88, whatever we have got, has the same form as 3.87 and establishes the result that the sum of two independent Gaussian random variables is also Gaussian. So this is a feature that makes the Gaussian random variable convenient to use in the engineering practice. Now let us take one more example. Let a random variable, we are considering here x to be exponential, and in that case, from the appendix A, okay, from the appendix A, we can write the exponential function fxx is equal to, that is the PDF of exponential function is lambda e to the power minus lambda x for x greater than or equal to 0 and 0 for x less than 0. At that time, the mu x will be equal to 1 by lambda, sigma x square is equal to 1 by lambda square, sigma the characteristic function phi x j omega is equal to lambda into lambda minus j omega minus square, and all these are from the appendix A. And this is what we have there. This is the fxx, which we considered mu x, sigma x, and then the characteristic function. This can be written as lambda into lambda minus j omega inverse. Okay, just another way of writing the same thing. So having written that, then let w be the sum of two independent observations of x, that is w is equal to x1 plus x2. Then fww, that is the what you call the PDF of w over here, will be the convolution of the PDF of x1 with the PDF of x2. And that's what is written over here, 0 to w lambda. So because it is greater than 0, hence we have 0 to w lambda e to the power of minus lambda x multiplied by lambda into e to the power of minus lambda w minus x. Okay, that is the convolution. So therefore, now if you simplify this, this will become e to the power of minus lambda w, and e to the power of minus lambda w has nothing to do with dx, hence it will come out, and lambda square also will come out. Integral of dx with limit 0 to w will just correspond to w, and hence we'll get this. Now this is similar to the Erlang random variable of the order 2. So let us see the Erlang random variable. Okay, Erlang random variable, and that turns out to be this: lambda to the power k, x to the power k minus 1, e to the power of lambda x divided by k minus 1 factorial, comma x is greater than or equal to 0, and 0 for x less than 0. Under that condition, when the PDF is this, mu x will be equal to k by lambda, when the what you call PDF is here lambda to the power k. So we have there lambda square. So therefore it will be 2 by lambda. The sigma x square is k by lambda square, and k value is equal to 2 in our case. In our case, k is equal to 2. So you can see that we have lambda square. So therefore, the what you call mu w will be equal to 2 by lambda, and sigma w square is equal to 2 by lambda square. So this gives us the whole figure of fxx with then the convolution of both of them together, that is the Erlang function. This is the exponential functions, exponential function fxx, exponential function fx of w minus x, and you take the convolution of both of them, that is this, you'll get the Erlang function, which is like this. So